This is where we are in Canvas. You can see today we're going to go over work notes or notes on work. Once we finish the notes work, there is an exit ticket. It's like a warm-up, but it's going to be done at the end of class based on the stuff we learned today. Once we get to that, I'm going to turn you guys loose. You don't have to hang out in the Zoom. Before next class, I want you to look at our STAIR lab. There is a worksheet involved, and we created a video. I was holding the camera. Mr. Hennessy was going up and down the stairs for you guys since we're not together, not doing labs together. And then it actually stars my youngest daughter holding a stopwatch. So you can see a cutie little girl with the face mask on, trying to do her best to participate in teaching because she actually wants to be a teacher, amazingly enough. At the bottom of this, it says homework for this unit. This does not mean it's due next class. This is something that I want you to ongoing work on as we go through work. Okay, so you're just getting the worksheets ahead of time. If you've got time and you want to just get as far as you can, great. If you're overwhelmed with what's going on in your other classes, just know it's not due next class. It'll just be one of those things where you come to tutorials, I got a question. We start class, I got a question. But it's not demanded that it's completed by next class. What I do want to see completed is a STAIR lab. I want you to have this opportunity to look at a lab, to see what it would have looked like to perform it, and then what data you get from it. Okay. I see something, since I haven't started writing, I can actually still see this. It says, when do you have tutorials? As a team, we have tutorials every day before school and after school, except for Monday morning, Friday afternoon. Specifically me, I have them Monday after school, Tuesday morning, Thursday morning. But Mr. Hennessy is an excellent teacher, and Miss Doyle has her own perspective as well, so that we have an ability. She's an excellent teacher too. I'm just saying we have our own ways of looking about things. So if you hear it from me and you're like, I'm not sure, hearing it from them by hearing it a different way, it's always beneficial. So don't hesitate to say, hey, I only want to see your tutorials. We've got tutorials every morning, every afternoon, except for first of the week, Monday morning, end of week, Friday afternoon. Sometimes I do them on the weekends when there's a big demand, and especially if there's a test on a Monday, there's always a big demand over the weekend. Last weekend, there was only one person that asked me on Friday, and like two asked me between Saturday and Sunday, and my weekend had just gotten over full. Will there be a test over work this 9 weeks? Ooh, that's a good question. How many more this between now and Thanksgiving? I think so. Yeah, I think so. We can look in the calendars once we get done with this. I have to open the calendar and see it, but I'm pretty sure we do something before Thanksgiving break because we still have 2 weeks. 2 weeks, if we didn't have a test, I would be worried if I were you, because the longer we go, the more material stacks up, right? And we don't want so much material that it becomes overwhelming to get through a test. If I was you, I'd want to test every other day. So it's okay, it's just little, right? Because we've only talked about a little. Anyway, let's get into the new stuff. Let's get into work. So if you ever had a job, you kind of know what work is, right? At least you feel like you know what work is because having a job feels like work. Well, let's actually talk about work. This will be work and energy. If you're taking notes, if you're recording anything on paper or electronically. Here, let me just zoom this in a touch. There we go. So I'm just going to call this work and energy. Work and energy. So I got to have energy to do work. Well, sort of. Okay, so let's define work. Let me dismiss that. Work is going to be applying a force to move an object. It's not all of it, but let me write that. Applying a force to move an object over a certain distance. Now, I'm going to add to this, it must be in the plane of motion. That force must be. Okay, I'm going to stop my share just a second because we'll have a short discussion. And I mean short. So when I think of work and I think of students that work, a lot of them are either waiters or waitresses. They're staff at restaurants, right? And They work at the restaurant. Now, when let's say a waitress is carrying food out to the people that are dining, they've got a tray and they're holding the tray while they walk, correct? Or you got to agree or not agree? Like move your heads. That's what they do, right? Okay, I'll pretend like you're agreeing. So if you've got a waitress and she's applying a force and she has a direction of motion, is she doing work based on physics? Now I want to hear you. Unmute.
Sorry, can you ask the question again?
Absolutely.
Oh, unless Tejas.
So a waitress, when she's carrying the food tray out to the diners at a restaurant, she's applying a force, she's moving in a direction. Is she doing work?
I think yes.
Yeah.
One person thinks yes. Who else?
I think yes,
I
because
think
the
yes.
object's moving.
Yeah, I think I agree.
I also
Okay,
There's-
so for anybody that you know that's a waiter or waitress, you can tell them they do no work, all right? Because their force applied is up to hold that tray up, right? Their direction is forward. Those are perpendicular. And if we go back to our definition, work is applying a force to move an object over a certain distance, and that distance and force have to be in the same plane. The force of a waiter or waitress is up. If you can see my hand, I'm like pushing up, I'm holding the tray up, but I'm walking forward. Those are perpendicular. That means no work. The force applied has to be in the plane of motion. Force applied has to be in the plane of motion for it to be work.
What about the force normal? Because if she's applying a force on the tray, wouldn't there also be force normal, like pushing it
well,
down?
that would still not be left and right, which is the direction she's moving.
You got it. She answered it for me. So the force applied has to be in the direction of motion in order for it to be work. Now, I feel bad for anybody that's a waiter and they're like, no, I bust my tail at work. Yes, that's a different kind of work. Okay. For physics, we're looking at the force applied in the direction that the motion was happening. So she is pushing up, the tray is pushing down. You know, her force normal of her hand to the tray is balancing the tray's force gravity down from the earth. All that's true, but that's vertical. Her movement's horizontal. Those are not parallel. Those are perpendicular, so no work. All right, so let's go back to the share. Let's do some more notes. Let's see how quickly we can get through this stuff. So share here. All right, we're back into the notes. So there's positive work and there's negative work. I'm going to scroll this up because I'm going to assume that we've absorbed the definition, and let's say what positive work is. So I'm going to say positive is this plus sign. Positive work is when the force is in the direction of displacement. Force is in direction of displacement. So that means negative work would be force is in opposite direction of displacement. All right, those little quote signs, those are just saying that it's the same as the above line. So work is force in the direction of displacement. That's positive work. Negative work, force is in the opposite direction of displacement. Okay, so if I'm pushing against something and it's moving in the direction that I'm pushing, positive work. If I'm trying to, if I walk away from my car in the parking lot and I forgot to put the brake on because I drive a stick shift. If I forget to put the brake on and it starts rolling backwards and I run behind the car and I start pushing, but it keeps rolling into me, I'm doing negative work. I'm pushing forward, it's rolling backwards, negative work. So positive work, the force is going in the same direction as the displacement. Negative work, opposite direction.
What if the forces are perpendicular, like the
If they're
waitress?
perpendicular, then there's no work being done. Perpendicular forces don't count.
Okay.
But Pi, what if the force is at an angle? What if it's at an angle? Let's look at that. All right, so I'm going to draw a hideous box. Well, maybe it's not hideous. Let's see. Here's my box. All right, that's my free body diagram. And what if my force is going this way? That's my force. I would say that the component, and let's say the motion, my velocity is that way. Okay, so my velocity is to the right, and this is like me pulling a little red wagon, right? It's moving to the right. I'm pulling up and to the right. So I'm going to say that the component of my force horizontal here is work. The component of the force that's going up, that is no work. So the force pulling upwards, because the object's moving horizontally, the force that's pulling vertically is not doing any work. But the component of the force that's pulling horizontally and the velocity is horizontal, that component of the force is doing some work. So if we put all this together, we can create a formula now. And we're going to say that work is equal to force times displacement times the cosine of theta. The cosine of theta is just that component of the force that's doing the work in this picture. Now, if there is no angle, if there's no angle, we could just simply say work is equal to force times displacement. If there's no angle. But if there's an angle, we're going to use the cosine of the angle. That's our first part of work. When we think of work, the very first thing I want to think of is force times displacement. Okay?
Mr. Watley,
Yes.
is work always horizontal?
Doesn't have to be. And it's not going to be in like 3 minutes, it won't be.
Okay.
We just used horizontal as our first example. We're going to transition from work now to energy, and we're going to define energy first, and then we're going to redefine work as a change in energy. And that's where we're going to see it as being vertical. So let's do that now, because you're asking about it, and because that's what I was going to do next anyway. Let's look at that. So let me scroll up. I don't know how much more page do I got a lot of room here. All right, so we've got gravitational potential energy. So this is going into energy. Let's just put gravitational potential energy. Gravitational potential energy. This is the energy of height. All right, energy of height. So if this is let's call this like a cliff, and this goes to the ground, and then here we are standing at the top of the cliff. So there we are. Whatever height this is will be our gravitational potential. Okay, whatever height that is off the ground. Now we've said that work is equal to FD cosine theta. And we've said that if there is no angle, work is equal to FD, right? Force times displacement. I'm just keeping this kind of on the forefront. You know, if I say it like 5 times, it must be important. Okay, now for height, the force is going to be mass times gravity. Because force, if we were to say, what is the force based on someone's height? It's their mass times gravity, because that's what's going to pull them down. So now the force has become mg. The distance is the height. So mgh. Here we're going to say that gravitational potential energy can be calculated by mgh. Mass, gravity, height. We can even say that, okay, well, work is equal to the change of energy, but we're going to say work can be mgh, which is equal to a change in gravitational potential energy. UG, all right, the capital U is potential. Capital U is potential. The little g, gravity, still gravity hadn't changed. So a change in gravitational potential energy is work, because work is not just force times displacement, it is a change of energy. Any change in energy requires work. And we can quantify the amount of work based on the amount of change of energy. I want to say it a few times so that it all sinks in, because you're like, oh, wait, work is force times displacement. Yes. But is work a change in energy? Yes. Well, which one is it? Depends on the question. It depends on the information provided. I can say that you are your mother's child. I can say that you are your father's child. I can say that you are a student at Independence. Well, which one are you? You're all those things. Same as work. It can be defined more than one way. All right. Now, it's not only change in potential energy, it is a change in kinetic energy, which we'll get to. But kinetic energy, well, I went straight to energy. Let me put kinetic in here. So kinetic energy is going to be with a K. And then we can just say overall, it's a change of energy, any energy. Work is change in energy. Seen right here. Work is a change in energy. Now, I mentioned kinetic energy, so let's define that. I don't want to get too far without defining what we're talking about. So I'm going to come up here in the top corner here and just say, oh, how about kinetic energy? Kinetic energy is going to be the energy of motion. We can define it by K is equal to 1/2 mv squared. M is still mass, V is still velocity. What do you think happens when our little stick figure guy is at the top of this cliff and he steps off of it? Now, this is a safe cliff. He's jumping into a body of water down below. You know, it's not too high. All the parameters are good. As he jumps and he goes downward, he's giving up his height. So his potential energy is going away. What do you think he's gaining as he goes down?
Kinetic energy.
Kinetic energy, because as he falls, his velocity is increasing. When he's at the top of the cliff, he's got all the height that he can have, but he's not moving, so he has no velocity. So at the top of the cliff, he is all potential energy. As he falls, right before his toe hits the water, he has no height, so he's got no potential energy. But right before his toe hits the water, he's hit his maximum velocity because he's got no more distance to fall. Now he's at max kinetic energy. So at the top, you're all potential. At the bottom, you're all kinetic. And you have now changed energy from potential to kinetic. How much work was done? How much energy was changed? You could say, how much potential energy did I start with? That's equal to how much kinetic energy I finished with. And then whatever value that is that went from potential to kinetic, that was work, because that was how much energy was changed. Okay.
Mr. Watley?
Yes, go for it.
Would you mind explaining the UK and E like in the formula?
The UK. Yeah, are you talking about right here?
Like the delta U, delta K, delta E.
Absolutely. So a change in potential energy, that's the delta UG. That is a change in potential energy. That is work. That's equal to the change in kinetic energy, which is delta K. That's equal to any change of energy. So a change in potential will equal a change in kinetic. A change in kinetic is a change in energy. Any of those changes is work. So that line was just to demonstrate that work can be a change of potential energy. It could be a change in kinetic energy. It could be change in any energy. Work is a change of energy. It's also force times displacement times cosine theta. If there's no theta, no angle, work is still force applied times displacement. That has not changed. But it's also defined as a change in energy. And we need to be flexible on that. We need to identify that work can be identified either way. I can identify you as a student. Yeah, I'm just saying, I can identify you as a student in my 1A class, but I can identify you as a student in your 2A class as well. You're still the same person. Okay. Let me give you one more energy because we are going to use springs. So let's do spring potential energy. Let's squeeze this in right here. Let's do spring potential. And then since it's a potential energy, we're going to use the U. The U is potential. This one's going to have a little S at the bottom. That's not a 5, that's an S. So spring potential is equal to 1/2 K, which is your spring constant. We remember spring constants from Hooke's law, times x squared. Now, the x for a spring is the displacement from its equilibrium position, whether it's compressed or stretched. How far is it from its happy equilibrium chilling, Saturday afternoon position? How far is it from that? That's your x. The k is that spring's constant. And the spring constant goes back to Hooke's law, so don't forget about that. Now we've got 3 forms of energy. We've got gravitational potential, mgh. We've got kinetic energy, K equals 1/2 mv squared. We've got spring potential, 1/2 K times x squared.
Mr. Watley,
Yes.
is the x the distance from the equilibrium in the spring potential one, or is it from the? Oh, okay.
Yeah, from equilibrium. So if I stretch it, it's okay. Where was equilibrium to the stretch? Or if I compress it, where was equilibrium to how far is it from that equilibrium position now? So if I put a spring, let's say the spring was like my stylus, if you can still see my screen. My spring sits here normally. If I compress it, where's the end of the spring now? Or if I stretch it, where's the end of the spring now? So I can say, okay, from the end of the spring where it normally sits, how much has it been compressed or stretched? That is your x. All right, I've got a little bit less. Yeah, I think we're going to run longer than I thought we were, but that's okay because this is an important topic. The introduction of the topic sets the pace of how we're going to do in this unit. Let me tell you that total.
Mr. Watley,
Yes,
can you scroll back up to kinetic for a second?
absolutely. I'm going to see. Can I scroll to right there?
Yes.
Is that good?
Yes.
All right, perfect. I'm writing at the bottom of the screen right now so we can both work. I'm going to tell you that total mechanical energy must be conserved.
I'm good now.
Awesome. I'm going to scroll up. Now, mechanical energy is gravitational potential energy, that's mechanical energy. Kinetic energy, that's mechanical energy. Spring potential, that's mechanical energy. Now, what is not mechanical energy? Burning gasoline, that's chemical energy. Okay. Burning fuel in your car, that's converting chemical energy into mechanical energy. Okay, you're taking gasoline in the engine. It's using, well, let's assume you don't drive a Tesla. Okay, conventional car. You're using gasoline and air, and you're using a spark from a spark plug. You're compressing it. You're using the potential energy in the gasoline, and you're creating a mechanical energy within the engine that's turning your tires. Okay. But when I say total mechanical energy must be conserved, I'm not talking about every energy in the world, though energy must be conserved. We're only talking about the mechanical. So what is the mechanical? Potential, kinetic, spring potential, those things. So if we were to make a little chart and say, okay, for a closed system, for this little environment, this little ecosystem that we're talking about, what would that look like? Well, if this was our starting point and we had gravitational potential and kinetic, and we're going to make a little bar graph. And we said, well, initially we had this much gravitational potential, 4 blocks, and no kinetic. It's just like nothing. And this is step 1. Okay. And then going from step 1 to step 2, along the way, now we've got 2 blocks of gravitational potential. So that means for kinetic, trying to make sure that looks pretty, we must have 2 blocks. We're basically transferring the energy from gravitational potential to kinetic. This is for our guy jumping off the cliff, jumping into the water. As he's on the way down, this would be like step 2. Step 3 would be when he's all the way at the bottom. Here we've got no gravitational potential because it's all now kinetic. And this would be our UG, and this would be our K. Here we're showing the transfer of energy, but the total energy is conserved. Starts off on the top of the cliff, it's not moving, jumps off the cliff, everybody's cheering for him, he's falling halfway down, half of his gravitational potential is gone, but now it's been replaced with kinetic energy right as he's hitting the water, no more gravitational potential, all kinetic. Realized through velocity, because his mass hadn't changed, his height turned into velocity. Think of a roller coaster at Six Flags. Roller coaster at Six Flags might, if we were to diagram that, maybe it would look like this. If we had something like this, this would be like position 1 bar graph. This would be position 3 bar graph, and this would be position 2 bar graph. Because in position 1, it's all height. Position 3, it's all velocity. We don't have any more height. Position 2, somewhere in between. Somewhere in between. All right. If we're okay so far, what I'm going to do is I'm going to switch over and we're going to pace kind of quickly through what is listed as notes in Canvas, because I wanted to give you this with an explanation written all out. Let's go through these notes. There's like a couple of practice problems. They're simple. We're going to pace quickly through them. And then I'm going to give you like a minute and a half worth of notes on power. And that finishes our day. We'll definitely be done before 10 o'clock-ish. Okay. So let's go to this. All right, this is the sheet that we find in Canvas. I did not mean for my finger to make a mark. Let's see, dismiss. Eraser. All right. Here it says work. The work transferred when force acts on an object while an object moves a certain displacement. Okay, we know this. What is the equation for work? We know that work is equal to force times displacement. This is saying in the exact same direction because it's saying that there's no angle. If there's no angle, we don't have to worry about cosine theta, right? It's an exact same direction. What are the units for work? We haven't said this yet, but it is joules. Units for work could be joules. How much work is performed by an applied force when a 50 kilogram, all right, well, this is mass, push 15 meters, that's a displacement, with a force of 20 newtons. So I have a mass, a displacement, and a force. Well, I know that work is equal to force times displacement. So work would be equal to the force of 20 times the displacement of 15. So then I would have work is equal to 300 joules. Pretty straightforward. Using this as an example. Don't worry if I'm going a little bit too fast with these practice problems. I'll take this recording. It'll be in the Zoom recording will be in Canvas for you to review, for you to like play me in slow mode, right? Cool. Okay, what is the equation for work if the force and displacement are not exactly in the same direction? Here's where we said work is equal to force times displacement times the cosine of theta. All right, now we've got that equation. Let's look at the practice problem. A boy drags his little sister by her pigtails, of course, not that we would ever do that. That's just mean. A horizontal distance of 31 meters, okay, that's distance, by applying a 51 Newton force, or that's 51 Newtons, 25 degrees. Okay, so our theta is found right there. How much work is done by the boy? Okay, well, we know work is equal to force times displacement times cosine of theta. We would have work is equal to 81 times 31 times the cosine of 25. Now, someone did this for me at one moment in time and said that the answer would be 2276 joules. Hope they got it right, but at least we can see how to set it up. Now, I'm doing something a little bit faster. I'm just marking my variables in the question. Ideally, I'd put them out in the margins to kind of have it listed out. I still want to use my guess method where I'm identifying my given. And since I've got a big purple pen while I'm writing on the sheet, it helps me identify my given that way. And it's faster for us to get through this. How
Mr.
much
Watley,
work would he do if the force is directed parallel with the ground? Instead of pulling at 25 degrees above the horizontal, now he's going to pull straight without an angle. Well, without an angle, we know that work is equal to force times displacement. So we would simply have 81 times 31. And if they did their math correctly, they got 2511 joules. He would do more work by pulling straight than at the angle because the entire force is used instead of a component of the force. We should sort of get that. We understand that if you pull at an angle, only a component is being used, and a component is never as much as the whole. All right. That is, I think, the whole first half of that sheet. We're flying through this because we're geniuses. You guys are very, very smart. All right, now, next question says, if a force of 100 newtons is exerted on an object and no work is done. All right, so we've got a force, but work equals 0. So that means my work equals force times displacement. It's telling me that this is 0 is equal to 100 times something. Well, 100 times 0 would be 0. So that means my displacement has to be 0 to make that equation work. All right, so accelerated rapidly? No. Remain motionless? Well, that works. Decreased its velocity? No. Gained momentum? We hadn't even talked about momentum yet, so no. Remain motionless. If I have no displacement, no work. I can go outside of the auditorium is like through this window to my left. I can go out there and push on that brick wall until the cows come home. That's a really old saying. I can push on that brick wall until the bell rings. The wall's not going to move, so I'm doing no work. I can break a sweat. I can build up muscles. I can push as hard as I want to, but if that wall's not moving, I'm doing no work.
Mr. Watley,
Yes.
would you mind going back up and explaining the parallel to ground versus
This one right here.
yeah.
Absolutely. So in the first one, we're pulling at an angle, a 25-degree angle. So part of the force is horizontal, and let's see, the force was 81. So this would be 81 cosine 25. And that looks like I put, just go with me. So 81 cosine 25, that is the component of the force in the horizontal, which is the only direction we care about. Okay, down here, all of the force is done horizontal. So all of the force is 81. So in the first example, I use a component of the force because the force is at an angle. I only want the component of the force that is parallel to the direction of motion. So I use 81 cosine 25. In the second question, question B, since it's being done parallel to the ground, I can use the entire force because the entire force is parallel to the direction of motion. So in question A, I have less work because less force is being applied parallel to the direction of displacement. In question B, all the force is being used in the direction of motion, so I'm going to have a larger value. Did that help?
Yeah, so basically what you're saying is in the first scenario, the force was applied at 25 degrees above the horizontal. In the second scenario, it was the same force, but it just changed the angle and it was at like 0 above the horizontal.
Correct,
All
correct.
right.
And
Thank
we
you.
only care about the force that is parallel to the direction of displacement. And so since it's one has more than the other because we're able to use all of the force in the second example, we're going to have more work. Or
All
we
right.
would have
Got it.
done more work.
Thank you.
Absolutely. All right, so let's see how many more practice. There are 3-ish practice problems. Suppose your mass is 65 kilograms, so that's mass. If sitting straight in your chair raises the center of mass, okay, so this is your height. So the height change is 0.2 meters. Then how much work do you have? Well, we know that work is also a change in potential, and that potential, gravitational potential, and that is mgh. Okay, well, mass is 65 kilograms times gravity is 10 meters per second squared. Height in this case is 0.2 meters. So this should equal something like 0.00, oh no, I'm sorry. I'm looking at the wrong answer sheet. Oh, this should equal 130 joules. Okay, I'm going to scroll this up where it's still in view. Suppose that your eyelid has a mass of 15 grams. Okay, we don't do grams, we do kilograms. So here I'm going to put mass equals 0.015 kilograms. Is that right? Yes. And that when it is open, its center of mass is, okay, so now I've got a height but I don't use centimeters. So I'm going to come in here and say this is 0.01 meters. And how much work do you have to do to open your eyes? Okay, so we know that work can be change in potential, which would be mgh. Mass is 0.015 times g, which is 10, times the height, which would be 0.01 meters, 0.01. This is the one that I think is, yeah, number 2. Here, this is the one that they tell me the answer is 0.0015 joules. I'm looking to a sheet for the answers. I'm using the setup just between us. Kind of get the idea. We've used force times displacement times cosine theta. Now we're using a change in gravitational potential, mgh. Last question. Suppose your textbook has a mass of, okay, we don't use grams. So mass equals 1.1 kilograms. And that you need to raise it from your backpack floor up to your desk. Okay, perfect. So this is a height. And constant velocity, don't really care about that today. So how much work do you have to do? So we know that work is a change in gravitational potential. Gravitational potential is mgh. Mass is 1.1 times gravity is 10 times h, which is 0.7. Pretty sure you guys can do the math. If the person that did this sheet for me did the math correctly, they said it was 7.7 joules. Now, how much work does gravity do in this process? Unmute and give me an answer. How much work does gravity do in this process? Is gravity doing work in this process? Unmute. Come on, let's be brave. Unmute.
Yes.
It does
Yes.
negative work.
Okay, so I love that you're saying yes. How do we know gravity's doing work?
Because it's in the vertical plane.
Right, it's in the plane of motion. She's exactly right. Gravity's pulling down. Was this a book? Yeah, the book is going up. They're in the same plane. So how much work is gravity doing?
Negative work.
Negative work. What's the value? All right, so we've said, yes, it's doing work. Yes, doing work. And we've said it's negative work. But what's the number?
7.7.
Yes, it's still 7.7. It's still the same amount of work, but gravity's doing negative work because gravity is pulling down and the book's going up. We, as the person picking up the book, are doing positive work because our force is pulling up on the book and the book is going up. But the change in energy is still the same. Gravity's doing negative work. We're doing positive work. Very good job. Very good job. Okay, we're almost done. That's the end of that sheet. Now, I want to take the information we have. Let's summarize it briefly. Add in power, which is even more brief, and then we're done. It's a lot for the day. It really is. But the good thing is between now and next class, all you have to do is look at a lab. The video for the lab was 31 seconds long. Yes, it is that long. You're going to look at the lab sheet, go through it, and then just peruse work 1, 2, and 3 worksheets, knowing that they're not due for Tuesday. They're just simply something you're going to work on throughout next week. All right. So let's go and let's get the last bit of notes in. Go to a fresh sheet. Yes.
So for that last part, did you say that the work would be the same answer as the question before?
Yes, the work for gravity is the same number, but it's negative.
Okay.
It's negative. Because gravity's pulling down and the book went up, gravity's force is in the opposite direction of the displacement. So gravity's work is negative, but the value is still going to be the same because the amount of work done didn't change, because amount of work is change in energy, and change of energy was based on mgh. Does that make sense?
Yes. Thank you.
Okay. Yeah, no problem. It's one of those that you really have to like practice and wrap your mind around, because first time through, you might be a believer and be like, I got this. But most people are like, this guy ate too many Cheerios this morning or something with sugar in it because he seems way too happy. But the sun is shining and it's a Friday. So why aren't you happy? 8 days are the best days. All right, work and power. So I'm going to title these work and power. So this is work and power. Oh, my writing's horrible. All right, work and power. Now we've said for work, work can be equal to a change of kinetic energy. And then if I wanted to define that a certain way, like what would a change in kinetic energy look like? A change of kinetic energy would look like, I'm going to take my current 1/2 mv squared, and I'm going to subtract whatever my old kinetic energy was, which would be defined as 1/2 mv squared naught. Y'all remember the v naught for initial velocity? So if you have a change in velocity, that's a change in kinetic energy. So take whatever your current kinetic energy is, subtract whatever your old kinetic energy was, based on your mass hasn't changed, just your velocity changed. You do that subtraction, that's your change in kinetic energy, that's work. All right. We can also say that for work is equal to a change of gravitational potential, which is equal to mgh minus, well, we know mass isn't going to change. We know gravity's not going to change. It's height. That's what's going to change. So let's call this mgh naught. So what is my current gravitational potential? What was my gravitational potential? The only thing that's going to change is the height. Put it in the formula. You can solve for work.
Mr. Watley,
Yes.
for that first equation there, it's that would be 0 unless there's a change in velocity, right?
Right, right. There has to be a change in velocity. So for this one, it would be sort of like driving in your car and you sped up or you slowed down. Or you weren't moving at all and you started moving.
Okay, so if there was no acceleration, then there would be no work?
No, correct. Regarding kinetic energy. So if you don't change your velocity, you have no change in kinetic energy. And in that respect, there's no work being done. So if you put your car in cruise control where you maintain a velocity automatically for you, there's no work being done. A work is a change in energy. And if you're maintaining your velocity, you're not changing your kinetic energy because your kinetic energy is 1/2 mass times velocity squared.
Okay, thank you.
No problem. Don't worry. You're gonna get a lot of experience with this. It's become second nature before long. Last thing we're going to define is power. All right, so let's add in power. Okay, power is the amount of work done over a period of time. So power, the only thing we worry about power now is time. So let me write that. This is the amount of work done over a period of time. All right, let me turn the light back on. Got dark on us. Oh, there it goes. All right, so power, the amount of work done over a period of time. If we were to define the formula, we can say that power is equal to work divided by time. Now, we know that work can be defined as force times displacement. And I'm going to put delta x for my displacement, intentionally so. Okay, so just allow me to say that displacement is delta x. Displacement is a change in the x direction, okay? And it's still over time. And we've also said that it's work is a change of energy over, well, work being a change of energy, so power would be a change of energy over time. So power is work over time. Work is force times displacement. So power would be force times displacement over time. Work is a change of energy. So power is a change of energy over time. Okay. Work over time. Now, one thing I want to point out is if we look at this portion and bring it down just a touch, here we can say that power is equal to force times delta x over, this is supposed to be delta x over t, right? I'm just pulling the force out and I'm looking at delta x divided by t. Well, what's delta x divided by t? What's the change in position over? Yes, yes, velocity. So that means power is force times velocity. We were able to derive that just by looking at the formula. Now the unit for power, units are watts, which is really just joules over seconds, but we're going to use watts. So power is in watts. I'll give you a second to write that. We're going to go to our exit ticket, which is like a warm-up at the end of class. We'll take a look at that. We're going to discuss it out loud together. And then you know you've got the STAIR lab between now and Tuesday. And you've got 3 worksheets between now and let's say sometime end of next week-ish, but they're basically assigned for the whole unit.
Mr. Wiley, would it be fine to ask a question right now?
Absolutely. Ask a question all the time.
So I'm just a little confused on like the worksheet that we just did. You know how there was a question at the very end about gravity? Would you mind going back to that?
Right there.
Yeah, I didn't exactly understand how much work gravity does in the process.
Okay, so let me just ask you how much work was being done, period. Not by whom, how much work was being done?
I think 7.75.
Okay, so 7.7, whatever, 7.7 joules was being done because we know that was the change in gravitational potential, correct?
Right.
Okay, so it doesn't matter who did the work. We know that's the amount of work done, yes?
Right.
Okay, perfect. Now, your textbook was raised from the backpack to the desk, right? From the floor to the desk.
Right.
You pulled up on that book, so the force you applied was in the direction of the motion of the book. So that
Right.
means you did positive work, and then I said how much work was done. You said 7.7. So you did positive 7.7 joules of work. Now, because you applied a force. Now, gravity was also applying a force, but it was applying it downward. So gravity's force was in the opposite direction of motion. So that tells us that gravity's work was negative. And then we say, well, how much work did gravity do? Well, there's only one amount of work done, 7.7, because that was the change of energy. So then we would ask, how much work did gravity do? Well, gravity's force wasn't at an angle. It was completely in line with the movement of the book. It was in the opposite direction. The work done was 7.7. Since force was in the opposite direction of motion, gravity did negative 7.7 joules of work. We did positive 7.7 joules of work. This isn't a balancing equation. This isn't like, well, net work was 0. No, this isn't a free body diagram. We're not doing net sum of work. What we're saying is that, was there a force applied upward? That was positive work. Was there a force applied downward? That was negative work because the object moved up. How much work was done? 7.7, based on the change of energy.
So, okay, so what you mean is they can be equal and it can still go up, like the joules. They can
Yes.
be equal. Okay.
Yes,
All right. Thank you.
absolutely. Because work isn't force. It's force times displacement. All right, let's go to the very end of this. This is our end of class warm-up, also known as a, what do I call it? Exit ticket. All right, so I want you to participate orally. I want to hear a lot of voices. So this is Friday. I'm letting you out of class 30 minutes early, so unmute. Let me see everybody's unmute. Ridwan, unmute. There we go, nice and loud. That was awesome. Okay, so Jason and Brent race up a hill that's 30 meters high. It's a path 60 meters, while Brent uses a longer path that's 100 meters long. It takes Jason 40 seconds while Brent runs up this path shorter time. They both start from rest at the same height and stop at the top. They have the same weight. All right, now, who's doing more work, Jason or Brent?
Same.
Don't look on canvas. Who's doing more work?
I think
They're
it's
the
the
same.
same.
Should be the same. Yeah.
Why are they the same? Y'all aren't cheating, right? Y'all aren't looking on canvas for the answer, are you?
Because they're going
Same
the
height.
same height
Same hill.
and they
Same
have
weight.
the same weight.
Potential energy, right? Here, what we're looking at is they're starting at the same bottom portion and they're going to the same height, right? And I love that you guys all said the right answer because it's supposed to lead you and say, well, you know, Jason's going up steeper where Brent's got a little bit easier route about it. But you're absolutely right. They're doing the same amount of work because the change in gravitational potential for them is the same. So then let's scroll this. Oh, I'm scrolling on the wrong sheet. So what about the power?
Mr. Watley,
Yes,
are we talking about the vertical work they do?
yes.
Yes.
Okay. So
Now, what about this? What about the power generated? Which one used more power?
Jason?
All right, so I'm going to scroll this back so you can see all the
Yeah.
information. Which one used more power?
Brent,
Brent.
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 Oh, Jason.
Jason.
Brent.
Didn't Brent use more power?
Brent, yeah.
'Cause
Why would
Jason
Brent
took
use
the
more power?
Because
finished
he
it
has less
faster, meaning
seconds.
he had to go faster to finish it.
Yeah,
Right.
how
They-
many hours? The work divided by time, man.
Yeah, because the work is equal between the two. Work is the same. So with Brent, you're dividing by 30 as your time. Jason, you're dividing by 40. So if you divide by a smaller number, you're going to end up with more power. So Brent has more power because you're dividing by a smaller number. So Brent had more power, Jason had less power. They both had the same amount of work. All right, this example is explained in Canvas. Let's go back over to that. It's called the work power exit ticket. It's something just to generate some thought. We got work done. I think it's because we had longer to explain it and talk about it and get used to it. It seemed like all the answers I heard were correct. When we got to power, we had a little bit stop down, which is normal because we only talked about power for like 12 seconds. Between now and next class, look at the lab, watch the cute little video. It has a beautiful little 10-year-old girl, so make sure that you watch the video for her benefit. Just kidding. Do the lab worksheet so you have that experience, and then work on work 1, 2, or 3 the best you can between now and next class. It's not due for next class, but you can come to class with questions.